Welcome back to Office Hours with Mr. Clark. So today we're going to be looking at wave theory and some quantum mechanics, some really low-level back of the envelope quantum mechanics. Quantum mechanics is a very complex field, chemistry and as well as physics, kind of area where chemistry and physics kind of merge. We're talking about atomic structure, electrons, protons, neutrons, all the things that's the really foundation of everything of matter, right? Whether it's non-living matter or living matter. But we're gonna start really basic. We're gonna look at the some wave theory. Share my screen here. Whiteboard. So, so let's talk about waves. So we've all experienced waves, whether like waves on a lake, an ocean, some ripples on a pond. And waves are fun unless they become like dangerous, like hurricane force waves. Yeah, due to, hurricane force winds. But we see cool waves like when people are surfing and the wave crests and they're surfing through the cylinder. So with waves, the distance between these two high points, we call them crests. And this here we call a trough, the low point. The distance between these two is lambda. So lambda is the wavelength. That's meters. The frequency, or nu, so it's pronounced nu, it's a Greek letter. Um, Lambda is spelled M-A-M, lambda. Right, looks like an H. Frequency is waves generated per second. The unit is the hertz, or reciprocal seconds. So if think about wavelength and frequency, you notice that as wavelength increases, frequency decreases. So when you have very long wavelengths, you can see it on a lake. You don't have that many crests. You don't see that many crests. When you have very short wavelength, you see a bunch of crests, right? Um, so they're inverse of each other. So with electromagnetic waves, electromagnetic waves, these waves are called electromagnetic because they have electric and magnetic components. Travel perpendicular to each other, perpendicular. So these waves all travel at the speed of light, c, which is approximately 3.0 times 10 to the 8 meters per second. So if you look at general waves or the sound waves, waves of the ocean, always, the speed of always equal to the frequency times the wavelength. We can say that with certainty. With electromagnetic waves, that speed is equal to c, the speed of light. They all travel at the same speed. And we're going to talk about electromagnetic waves in a second. So the frequency times lambda. So let's look at an example. So if I have light that's traveling frequency of 7.30 10 to the 14 reciprocal seconds, what is my wavelength? So C is equal to frequency times wavelength. I want wavelength that's going to be C over frequency. So 3.0 times 10 to the 8 meters per second over 7.30 times 10 to the 14. To the 14 reciprocal seconds. Seconds cancel. And you do your math. Pull out my calculator here. It's 3 divided by 7.30. That gives me 4.1 times 10 to the minus 7. 0.11 times 10 to the minus 7 meters. So 366 here and a 366 here. That's how you manipulate that equation. So we can solve for wavelength or frequency. Let's talk about the electromagnetic spectrum. Actually, no. Let's talk about some more waves theory. Then we'll get to electromagnetic spectrum. I wanted to introduce electromagnetic waves just because we want to talk about the fact that they all travel at the speed of light, right? But so we talked about frequency, wavelength, amplitude of the wave. This is an amplitude. That's a distance from the midline. The midline is where the wave changes direction, right? So here it's going down, here's going up. So the midline, distance between the midline and the height of the wave, or down to the trough. We call that an amplitude. There are other concepts, like for example, refraction. Rays change then traveling different media. Different densities. So we can see this phenomenon, for example, when you're standing in a pool of water and the part of your body that's submerged looks bigger than the part that's above the water. That's because the light waves, when they're traveling in air compared to water, those have two very different densities. So you're going to have bending, um, and the bending called, also there's a bending, and there's also change in wavelength. Diffraction have bending of waves around an object through a small opening. So, for example, you have an object, which could be a wall, and here's its waves. The waves will bend. That's how we can hear around a wall, sound waves. The bending does depend on the wavelength. So waves with very tiny wavelengths, like light, for example, won't bend around a wall, so we can't see around a wall. But light will bend if you have a really tiny pinhole type opening. We can see the phenomena of light bending. And this is really how an experiment that was done, some more involved experiment, which I won't get into, but it's a very popular one in most CC, most chemistry and physics books. It was shown that light can bend, through a small opening. So we do notice that phenomena with light, but it has to be a really tiny pinhole type opening. That's diffraction, interference. This is when you have overlapping of waves. So if you have waves that are generated simultaneously, let's see, one go from one direction, you have these overlaps. So if you have two crests overlapping, you get a bigger crest. If you have a crest and a trough, what do you think you get if those two overlap? Yep, they cancel. So we can see the interference phenomenon if you're at a place where there are like multiple sound speakers blasting, music or voices, and you're walking through the room. There are points where the sound sounds muffled, and there are points where it sounds very loud, depending on where you are in the room. That's interference. Right? So let's look at our electromagnetic waves. So there are a few of them that we have to know. So it's radio, microwave. These are electromagnetic or EM waves. And we're going to go back to these. Or if we talk about them traveling the speed of light, we're going to go into a little more detail. Radio, microwaves, infrared, and a lot of these we know from daily life. Visible, UV, X-rays, and gamma rays. So there's a little silly thing I devised to help you remember. So red milk is very uber extra gross. All right. So red milk is very uber extra gross. So red, radio, and microwaves, high infrared, very visible, uber, UV, extra, gamma rays, gross. So if we're thinking about wavelength, so wavelength, the lambda increases as we go towards radio. So radio waves are really bigger wavelengths compared to, say, gamma rays. And frequency decreases, which we expect, right? We talked about that earlier. Now, something else we're going to introduce, energy. The energy of these waves decreases in this direction. So the opposite is also true. Wavelength decreases, frequency increases, and energy also increases. So if we're comparing frequency to energy, energy and frequency move in the same direction. Wavelength moves in the opposite direction. So of course, there's an equation for that. And it is E is equal to H times lambda. H is Planck's constant. Planck's constant. So what is Planck's constant? We can easily, that's typically something that you will be given on test. You don't have to try to memorize it. 6.626 times 10 to the minus 34 joules second. So Planck is a scientist that did a lot of work in quantum mechanics, and he came up with the theory of the idea of quantum, meaning these packets of energy that are emitted when, excuse me, emitted from matter or absorbed by matter. So when we see light coming from a light bulb, there's the idea that these light is coming out, right, that we see in these discrete amounts of energy. It's not random and it's not continuous, meaning we don't go from, zero all the way up to whatever highest is. Like there's like specific energies depending on the material that's being energized. So like we're running electricity through these light bulb filaments, and they're giving off these different color light, depending on the metal. So scientists notice that depending on the metal, you can get these different colors, and then they can relate that to energy. So the energy that's absorbed or emitted by matter is they come in these discrete amounts. Kind of like you can think of cars on a freeway. If you're counting cars, you say, okay, there's like 5 cars that has passed by, or 4 or 3. You don't say, oh, there's 5.5 cars or 5 3/4 cars. And that's kind of how you want to look at the quantum. So E equals H times mu, another equation. So we can do some math here. So let's look to see how we can, like a problem we can solve here. So let's find frequency of light with energy 3.28 times 10 to the minus 19 joule. And we can also find a wavelength too if we wanted to. Let's say wavelength as well. So now if we use equals H times mu, mu is equal to 3.28 times 10 to the minus 19 joules over 6.626 times 10 to the minus 34 to a second, to a cancel. We let the reciprocal seconds, and we do some math, and we get 4.95 times 10 to the 14 reciprocal seconds. That's a frequency. Let's find the wavelength for that. So C is equal to lambda times frequency. So lambda is equal to C over frequency, 3.00 meters per second, 4.95 times 10 to the 14. Do that math, we're going to get it's going to be 6.06 times 10 to the minus 7 meters. So now a popular unit for, excuse me, wavelength is nanometers. Because a lot of wavelengths are so tiny, we don't always feel like writing all this big number. So we can convert that to nanometers, 6.06 times 10 to the minus 7 meters. So 1 nanometer is equal to 1 times 10 to the minus 9 meters. All right, so there's about 1 billion nanometers in 1 meter. So 6.06 divided by that gives us 606 nanometers. And that is the wavelength, so we can actually tell what color this light is. I think it's about orange to the red-orange region of the visible spectrum. So that's how we can manipulate the equals lambda, excuse me, h in the equation. So there is another equation that you can look at. One more equation, yes, and it's the Broglie's so something that came out of quantum theory was that light and other electromagnetic radiation move as waves, right? So that was proven by different experiments. But also something that Einstein was able to explain was that they also move, they also have particular nature, meaning that you can conceptualize them as these packets of energy that also have mass, not appreciable mass, not something you can weigh on a scale, but still mass. And Einstein proved that with a photoelectric effect. So, which is a separate thing to discuss. But de Broglie, he conjectured that, well, if waves like these UV rays or light or visible can also have this particular matter as well as energy, maybe all matter can also travel as waves, like a baseball, for example, right? So de Broglie's equation, you can calculate the wavelength of any moving object. So h, that's Planck's constant, which we already know. V is speed, not frequency. This is a speed meters per second. And then m is mass in kilograms. So now we have an equation that relates mass and waves. You can even think about Einstein's Popper equation equals mc squared. You have energy and mass in the same equation. So we can calculate the wavelength of anything. So let's take a baseball, moving at, let's just say 50 meters per second. It's thrown. Right? And let's say the baseball weighs, the baseball weighs 35 grams, right? What wavelength is this baseball moving at? So first, gotta convert 35 grams to kilograms. That's gonna be 1, 2, so it's gonna be 0.035 kilograms. And then we're ready to throw in an equation. The Planck's constant is always gonna be the same, 61626, 10 to minus 34. Then we have 0.035 kg times 50 meters per second. So now this Planck's constant took in joules per second. We can break down joules into kilograms and meters and seconds because you think about joule, the joule, we can compare that to force moving through a distance, which is force equal to kilograms times acceleration. You think of Newton's second law of motion. So we can, I won't show you that in this video. It's gonna, take a little more time than we need. But just trust me in that everything will cancel except meters. Right. And then we just do the math. So my wavelength is 3.78 times 10 to the minus 34 meters, right? So this is a really small wavelength that we can't even measure. And we actually, sound make this 2 6 figs. So that should be 3.8 times 10 to the 34 meters, which will be my answer. So very small, tiny wavelengths. It's not something that we can appreciably measure. But if you think of something like that's really tiny, so tiny particles like electrons and protons, we can actually measure their wavelengths. Because the mass of electron is really small. So if know the speed and you can do the math and you can actually calculate appreciable wavelength, something you can measure. And the experiments have been done to show that electrons actually do travel its ways. Davison/Germer did that experiment. So those are the 3 equations, and then it's a little bit of wave theory. So on our next video, we'll look at go into some more detail about orbitals and things of that nature. Until next time, I'll just start with Dr. Clark.